Hi there, Mr. Sutton here with the AB Calculus 615 homework solutions on integration with respect to y. On this problem, we're trying to get the area of the region enclosed by these functions. So this is a calculator-based problem, so let's go to Desmos and graph all these out. We have f of y equals y squared minus 1, so we have a sideways parabola, and g of y equals the square root of y. So got one of these sort of square root sort of functions, and we also have y equals 1, this line here. So the area enclosed by all of these is this little sliver in here. So there's a picture of what we're looking for, and we just want the area of that. Now if we tried to do this from left to right sort of integration with respect to x, it would be a huge pain. We'd have to convert these into f of x sorts of functions, and we have a change in function right here. It changes from basically the line y equals 1 into this square root sort of line. So we're going to do integration with respect to y instead. In order to do this, we've already got functions in terms of y. We do need to find limits of integration that are y values. The bottom y value here of the bounded region is just 1. They kind of gave us that. But we need to figure out where these functions are intersecting up here to get that upper limit. So we're going to figure out where f of y and g of y intersect. And I'm going to go on the calculator and do this now. So just clicking on either of those functions and clicking on this gray dot here, it looks like the y value, where those are crossing, happens at 1.490. So I'm going to copy that, and I'm going to paste that and call it a point. You can call it p or whatever else you want, but I'm going to store that value. So I've got y equals p, approximately 1.4902. And now I'm going to take the integral from 1 to p of, I need to do my rightmost function minus the left function. So that's going to be this g of y minus f of y. And I'll put a dy in there. And then it's back to Desmos to actually plug all that in. So going down here, we've got integral. And let me just go down there from 1 to p of g of y minus f of y, close parentheses, dy. And that comes out to about 0.267. On this calculator-based problem, they want us to find the area of this enclosed region between f of x, g of x, and y equals 3. So let's go ahead and graph these and see what we're dealing with. So on Desmos, let me do f of x equals square root of x plus 2. G of x is just x. And then we have y equals 3. So it's this area in here. Now if you take a close look at this, if I take the functions the way they are and do some integration using dx, integration with respect to the x-axis, we have a change in function right at this spot right here. So I'm going to have to switch my bottom function about halfway through and use two integrals. Instead of doing that, another way to do this would be to integrate with respect to the y-axis here. So if I do left-right strips, horizontal strips instead of vertical strips, then I can just use two functions instead of having to mess around with a change of functions. So that's actually what I'm going to do. I'm going to rewrite these in terms of y. So for this first one, to get x by itself, I would subtract 2 and square both sides. So this would be y minus 2 squared if I convert this f of x function into an f of y function. And for g, well, I can just say x equals y basically, f of y equals y. And then y equals 3 is still itself. So going back and graphing these just to make sure we have the same stuff. Now I have, let me just get them in here. F of y equals, we said, y minus 2 squared. Okay, y minus 2 squared. And we also have g of y equals y. So we still have that same area, now just in terms of y. Now we also need to get some limits of integration. Our bottom y value is this y equals 3 that they gave us, for the top value, it looks like 4. But let me just go on here and double check. If I click on there, that is the y value 4, so that works out. So we have f of y equals g of y at y equals 4. So now I just need to take the integral from 3 to 4 of, and this is going to be g of y minus f of y, rightmost function minus leftmost function, dy. Let me go on Desmos and do all that. Let me just move so I can see. And come on. There we go. Now I can see. So we have integral from 3 to 4. Open a parentheses. We have g of y minus f of y, close parentheses, and then dy comes out to about 1.167. For this calculator-based problem, they want us to find the volume of the solid obtained by rotating the region bounded by these curves about x equals 3. Since it's calculator-based, let's graph all this and see what we're dealing with. So on Desmos, I'm going to do f of y equals 3 minus y. It's just a line. We have x equals 0, which is just the y-axis, and y equals 0, which is just the x-axis. And we're going about x equals 3. So let me put that in there as well. X equals 3, and that's this line out here. I'm going to just go to my gear and change the way that looks, make it dashed so that it's more obvious to me that that is the region that's the line that we're revolving around. So here's another look. It's this bounded region in here being revolved around this x equals 3 line. In order to make this happen, I'm going to have to use washers because I have this space between the bounded region and the axis of symmetry. So I'm going to use a of y equals pi times big R squared minus little r squared. For the big R squared, I've got the distance from my axis to the further away part of the bounded region. So this is the distance between 3 and 0 for x values. So that's just going to be 3 squared that I'm using for big R squared. And then for little r squared, that's the distance between 3 and this f of y function. So 3 minus f of y quantity squared for that one. All right, let me go and integrate this. So in order to do that, I have to go from the y value 0 to the y value 3 up here. So integral from 0 to 3 of a of y dy, and let's plug all this in Desmos now. So let me put my a of y function in there, and let me just move so I can see it. So we have a of y equaling pi, parentheses, 3 squared minus, parentheses, 3 minus f of y, close that parentheses, square that, and then close the big parentheses. So we've got a of y, and now let me do integral from 0 to 3 of a of y dy, comes out to 56.549.
On this problem, I want to take the area between square root of e to the y, the y-axis and the x-axis, and this horizontal line at y equals 1, that area, and find the volume when I spin this around the y-axis. So the first part of this that's kind of tricky is this is a no calculator problem. And when you're trying to do one of these problems, visualizing it's half the battle, and that's going to be tough without a calculator on this. So here's how we could do this without a calculator. If you don't know what a function looks like when it's expressed in terms of y, it sometimes helps to express it in terms of x and see if it's a familiar function. So this one, for example, if I want to get the input value to be x and isolate y to get this as a function of x, I can square both sides. So I'll call this x squared equals e to the y. And then if I want to make this y equals something with an x, I need to take the ln of both sides to get y out of the exponent. So on one side, I'm going to just have y. On the other side, I've got ln of x squared, which I can write as 2 ln of x if I pop out that 2. So we know what ln looks like, basically. So just sketching this out, I've got a logarithmic function, and I've got this horizontal line at y equals 1, so it looks something like this. And I need to find the volume when I spin this little area in here around the y-axis. Now that I've got a visual of what's going on, let's see how we could do this. Since my bounded area is flush against the axis of revolution, since the axis is one of its boundaries, that means I can use disks instead of washers for this, so that makes it a little bit easier. So then I end up with a of y equals pi r squared, and for my radius now, that's just the distance from the y-axis to my function here, so that's just radical e to the y that I'm squaring in there. Since I'm doing this by hand, I'm actually going to simplify this to pi e to the y. And now it's time for my integral. So my limits of integration, we're going from 0 to 1 for y values. So integral from 0 to 1, this is going to give us the volume now. And inside here, I'm going to have my a of y function, which, since again I'm doing this by hand, I'll actually write in there. So pi e to the y and then dy. The antiderivative of this is actually not so bad. It's also pi times e to the y. And I'm evaluating that from 0 to 1. So to do this, I'm going to yank out that pi. And inside, I've now got e to the 1 minus e to the 0. You could leave it like this, or if you want to simplify it, this is pi times e minus, this is really pi times 1, so minus pi. For this problem, we have this region R in the first quadrant enclosed by these lines in the graph of this parabola. And we want the volume of this thing when we revolve R around the y-axis. So this is a no calculator problem, but we can at least visualize what this looks like. We have a upwards opening parabola above the x-axis. We have a horizontal line through 5, and we have the y-axis itself here. So here's a basic sketch of what's going on. Now we only wanted the first quadrant out of all this. So this is the area right in here, and we're revolving this little area around the y-axis. Okay, so first thing we're going to do, since they gave us a function in terms of x, and we're going around the y-axis, we want to re-express this function in terms of y. So I'm going to start by subtracting 1 from both sides and then square rooting, and I can write x equals square root of y minus 1. So now I can use this to figure out x values, which is exactly what I'm going to need if I'm going to be integrating anything with respect to y. Next, I need an area formula for the cross sections. Since my bounded region here is flush against the axis of revolution, since the axis is one of its boundaries, we're going to be using disks on this one, pancakes. So I'm going to write a of y equals pi r squared, and then r is just going to be the distance from my axis to this function here, which is just the square root of y minus 1. So I'll write pi times radical y minus 1 squared. Now, since I'm doing this by hand, because this is a no calculator problem, I am going to simplify this when I put it in an integral. The only other thing I have to keep track of is what are my limits of integration. So my lower y value in this one is definitely 1, and then for the upper one we've got 5. The volume then is going to be the integral from 1 to 5, and I'm also going to take this pi outside here just so I don't have to mess with it inside the integral. And then inside I'm just going to have the, let's see, square and square root cancel, so this is going to be y minus 1 dy. All right, antiderivative, I'm going to have pi on the outside, and on the inside of my evaluation box, I've got 1/2 y squared minus y. And again, we're going from a 1 to 5 for this one. So I'm going to have pi times all this stuff with 5 plugged in, and we have a big parentheses that we're opening for this, and we're going to be subtracting all this stuff with 1 plugged in. So if this were a free response problem, we could just stop here and call it a day. However, you have answer choices to choose from, so we do need to simplify this as far as it'll go. So for my first brackets here, this is going to be 25 over 2 minus 5. That's essentially 25 over 2 minus 10 over 2. That's going to be 15 over 2 there. For this next one, we've got 1/2 minus 1, which is just negative 1/2. But wait, we have a minus outside, so that's actually plus 1/2 when all the dust settles. 15 halves plus 1/2 is 16 halves, or just simply 8. Pi times 8 is 8 pi. So that's going to be choice B.
For this calculator-based problem, we want to know the volume of the solid generated within the region bounded by x equals square root of y minus 2, and the lines x equals 0 and y is revolved around the y-axis. So let's go to Desmos and graph all this. So we have x equals square root of y minus 2. That's what it looks like there. And then we have x equals 0, which is just the y-axis. We have the horizontal line y equals 5 up here. And then we want to revolve this around the y-axis. So it's this bounded region revolved around the y-axis. Okay, well, since we are since our bounded region is flush, no gaps against our axis of revolution, we can use disks on this one. So we have our area formula, a of y equals pi r squared. And also, let's get our limits of integration. We're going from bottom to top here. The top one is going to be 5. The bottom one is whatever this y value is. If you set 0 equal to the square root of x minus 2, we come up with a y value of 2 out of that. So again, we're using disks. This is going to be pi times, and now for the radius, that's just the distance from the y-axis to this function, which is just the function square root of y minus 2. So let me go ahead and integrate that again from 2 to 5. And it's just this function, which I'm going to call a of y. Let's put all this in Desmos and see what it gives us. So we've got a of y equaling pi, and then we said square root of y minus 2, and that was being squared in a parentheses. So squared, great. And then integral from 2 to 5 of a of y dy comes out to 14.137, which is choice E.
On this no calculator problem, they're telling us the region enclosed by x squared and 2x is the base of some solid, and our cross-sections perpendicular to the y-axis are rectangles with a height of 3 times the base. We want an expression that gives us the volume of this solid. All right, so let's start with a visual here. It was a non-grapher question, but we could graph out x squared and 2x pretty quickly to get a picture that looks something like the following. So the big takeaway from here is that we have this bounded region here with 2x on top and x squared on the bottom. Okay, so we need to come up with a few things for this. For one thing, we need our area formula. Since we're dealing with rectangles, let's start with a of y equals base times height. And now it'd be nice if we just had this all expressed in terms of the base, because that's the side that we can actually talk about using y values. So our height, they said, is 3 times the base. So this is really b times 3b, which I can simplify to 3b squared. But I'm not quite done yet. I need to actually express this in terms of y to help me match something that's in the answer choices. So the base is going to be the distance, the horizontal distance, between these two functions here. The trouble is, my functions that I have up here are in terms of x, not y. So I'm getting outputs that are y values, not outputs that are horizontal x values. So I'm going to have to rewrite these. This first one I'm going to rewrite to be, let's see, this is going to be x equals the square root of y. So I'll call that exactly what I just said. And then this next one, we're going to have x equals y over 2. So now if I want the distance between these functions, which is the base of my rectangles, I'm just going to be using, let's see here, this is going to be from right minus left. We've got the square root of y minus y over 2. So we're doing 3 times that stuff squared. Now at this point, just thinking ahead a little bit, to get the volume from integrating all of these rectangles, we're going to take the integral with this inside of it. This is everything that's going inside the integral. The only thing we don't know is the limits of integration. If you look at the answer choices, you already actually have an integral with this exact thing in it. There's only one. It's choice A. And we have this little 3 that we just kind of pulled outside the integral, and that's okay too. So we could actually pick choice A at this point if we were pressed for time. But we also, if we wanted to, could go back and find the limits of integration. So that's just going to be where these two functions intersect in terms of y values. So we can actually take these two rewrites here and set them equal to each other. Radical y equals y over 2. Square both sides. We've got y equals y squared over 4. And then let's see, I'm going to multiply by 4. That's 4y equals y squared, and then I'll subtract 4y from both sides. Now we can solve by factoring. Just take out a y. So that gives us y values of 0 and 4. So then putting it all together, we have the integral from 0 to 4 of all of this stuff, which I'm just going to call a of y dy, but we know it's all this stuff. So again, that's going to come out to choice A.
On this calculator-based free response problem, R is the region in the first quadrant bounded by the graphs of y equals square root of x and y equals x over 3. They want us to find the area of R. Well, since it's calculator-based, let's plug this into Desmos and see exactly what kind of region we're dealing with. Oh, and when I do this, I'm going to rename this square root function to f of x, and I'm going to call this other one g of x. All right, so we have f of x equals square root of x, and g of x equals x over 3. So that's what we're dealing with. Now, if I'm trying to find the area here, I could definitely do this from left to right. I mean, at this point in the game, I'm always thinking, should I, integrate with respect to x or with respect to y? There's no advantage in integrating with respect to y at this point, so I'm just going to do this kind of the old-fashioned way. We're just going to do the integral from 0 to 9, and then we'll just do top function minus bottom function. So here we'll do f of x equals g of x. I'm showing on paper here that these equal each other. They intersect at 0 and 9. So those will be my limits of integration. So we'll be doing integral from 0 to 9 then of, and the top function was the square root function. So we're going to have f of x minus g of x dx. And let's just plug that in the calculator now. So let's do integral 0 to 9 parentheses f of x minus g of x, close parentheses, dx, comes out to exactly 4.5. For this part of the problem, part B, they want us to find the volume of the solid generated when R is rotated about the vertical line x equals -1. Well, this is a little bit of a shift here because if I'm going around a vertical line, that means I have to do integration with respect to the y-axis, or at least I need to do a dy sort of integral. So that means I need to get all of my functions in terms of y. So for this first one, what I was calling f of x equals square root of x, I'm going to rename this. I'm going to solve for x, and I'm going to say that f of y equals y squared, if I square both sides of that. So that's the f of y version of this f of x function. So we also have to do the same thing for y equals x over 3. If I solve for the x over here, then I can write f of y equals 3y. And that'll be my g of y function. All right, so let me go ahead and actually graph all this out on Desmos. So here's what I had originally in Desmos. We had f of x and g of x. I'm going to change this now to be f of y equals y squared. Let me just put an equals in there. And this upper part of it is what we had before. We also have kind of this phantom branch down here that wasn't part of the original function, but that's not really going to affect what we're doing on this problem. Now for the other one here, we're going to do g of y. Let me just erase all of that. G of y equals 3y. And we again have that line, nothing funny going on there. All right, we also have the vertical line x equals -1. Let me put that in there to see where it is. And that's over here. And if I want to be super fancy, I will change how that looks to be a dashed line just so I know it's my line of revolution here. So I've got this bounded region in here that we're rotating around this line. Since there's a space between my bounded area and my axis of revolution, I am going to need washers to make this happen here. So my formula, and actually before I even do my washer formula, let me figure out where these things are crossing to get my limits of integration. So f of y equals g of y, where? Well, going back here and just clicking on one of these, we see that these are crossing at the y values 0 and 3. We're looking at the y values here. So 0 and 3. All right, so now getting my washer formula, that's going to be a of y equals pi times big R squared minus little r squared. And I'm calling this a sub 1 because I looked ahead, and in part C there's another area formula I'm going to have to write that I don't want to mix up with this one. Okay, so what's my big R going to be? Well, big R, looking at my graph, that's the distance between the further away function and my axis of revolution. So that's the g of y, the 3y. So that's going to be just this distance from left to right. So we've got 3y, or g of y, minus negative 1. So in this case, that's going to be g of y plus 1. And I'm squaring that because that was big R. Little r, going back here, is this inner part. This is going to be f of y minus negative 1, f of y plus 1. So this is my area formula. Once I've got that entered in, I can just take the integral from 0 to 3 of a sub 1 of y dy. But I will need to do that on the calculator. So let me go back here, and we have a of y equals pi, parentheses, and in there, let me just do a couple squared parentheses. So here's one squared parentheses, and I'm going to subtract another squared parentheses and close it all. This is the overall structure of this thing because we've got a lot going on. Now in this first one, we had g of y plus 1. So g of y plus 1, there we go. And in this other one, we had f of y plus 1. And I don't even want to look at the graph at this point. It's just a mess. But let's deselect that so I don't have to look at it. All right, now let's do our integral. We were doing our integral from 0 to 3 of my area. So integral 0 to 3, a of y dy. And that's coming out to 130.062. For part C on this problem, the region R they're telling us now is the base of a solid. For this solid, cross-sections perpendicular to the y-axis. So again, we're doing y integration. Those are going to be squares. We want the volume of the solid. So let's go back to our graph. And I don't need this x equals negative 1 business anymore, so we can get rid of that. And can probably also get rid of most of this. I'm going to need an area formula at some point, so let me just kind of leave this open and ready to get another area formula. So this region in here that we found the area of before, this is now the base of a solid, and we've got some squares that are perpendicular to the y-axis. So these are like these are squares whose base is running left-right. These squares are just kind of popping out three-dimensionally. So what we're going to do is get the area of one of these squares and integrate it over the interval from 0 to 3. So general formula for square area, that's going to be s squared. And this is going to be my integral area formula, which I'm now calling a sub 2 of y. Now the base of the squares is just going to be the distance between these two functions, the f of y and the g of y. So we're just going to call that g of y minus f of y and then squared. And this is the right order here. We have further right minus further left. But just the way this is set up, since you're squaring it, you would actually get the same answer even if you messed up this order. Anyway, let's go ahead now and integrate that from 0 to 3. So this is going to be a sub 2 of y dy. Going back to the calculator, let me put my area formula as parentheses g of y minus f of y, and then close that and square it. And now my integral is giving me an answer of 8.1. So that'll be the volume of that solid.